A k-nearest neighbor graph tends to be more like a random graph than like a scale-free graph. And in particular, we want to look at graphs that are both scale-free and small world. An Erdos-Renyi random graph has n vertices. Again, n here is to be thought of as large, and has the property that for any two vertices chosen at random, there's a probability p that they are adjacent for some fixed p. Typically, we take the k from the k nearest neighbors and put it over n, and that gives us our probability p, because that gives us an expected degree of the random graph of k. If p is small, which it would be if n is very large and k is not so large, then the random graph tends to be disconnected with many components. As it gets larger, it tends to produce a connected random graph whose degrees are Poisson distributed for a large n. Remember, we're thinking in terms of k being much smaller than n. So k nearest neighbor graphs are approximately regular. In a regular graph, every node has the same degree, and the degree distribution is just a single bar. A random graph, an Erdos-Renyi random graph, which the word random graph will refer to from now on, is also called exponential, and it has an expected value of some k, but it tends to have a degree distribution that's Poisson distributed. It's not important you know what Poisson distributed is, just that the purple shape that you see there is typical of a Poisson distribution. Scale-free is much different, though. It's a power law distribution. There are hubs of higher degree, and not many of them. Most have smaller degree, but there are high degree hubs. So regular is definitely not scale-free. And the result of a k-nearest neighbor algorithm is very useful, very real-world, and very faithful representation of something, but it produces a graph that's not necessarily like the graphs that we would get from the real world itself. In particular, they tend to be closer to exponential than scale-free, and so we'd like to rewire a random graph or a k-nearest neighbor graph, because the k-nearest neighbor graph looks sort of like a random graph. We'd really like to rewire it so that its neighbor relationships are more real-world-like. But before we can do that, we need two new concepts. The first concept is the idea of a clustering coefficient. So if V is a vertex in a graph G, then the clustering coefficient is the number of pairs of neighbors that are adjacent to V that are also adjacent to each other, whereas the denominator is just the total number of pairs of neighbors. So let's look at an example from this regular graph. We choose a vertex, look at its neighborhood, and let's pull it out here where we can see it by itself. So there are 6 possible pairs of vertices that could be adjacent in the neighborhood of V. So those green vertices. However, there's only 1, 2 adjacencies. So there's 6 possible and 2 actual, and that's a third. Let's look at a scale-free example. Again, we've picked a vertex here, actually a hub vertex, and we choose the neighborhood. Again, let's look at it in inset. Now we have 7 vertices in the neighborhood, so there are actually 21 pairs of vertices that could be adjacent to each other in the neighborhood of V. But in this example, there's only one that actually is adjacent. Only one pair that are adjacent to each other in the neighborhood of V. So the clustering coefficient here is 1/21. Now we can also interpret the clustering coefficient in terms of the subgraph corresponding to V by looking at the number of actual triangles containing the vertex V divided by the number of possible triangles containing V. So in the first example, we've got 2 triangles, and there are 6 possible, so that's 2 over 6, and only 1 triangle, including V, in the second example, over 21 that are possible. Now here are some examples. If you have a hub, just a hub by itself with just vertices connected to the center V, then the clustering coefficient is 0. So a vertex could have a high degree but have a low or even 0 clustering coefficient. However, if you've got a vertex V and all of its neighbors are connected, then you've got a clustering coefficient of 1. The clustering coefficient of a graph is just the average of the clustering coefficient of the vertices. So we just take 1 over the number of vertices and add up all the clustering coefficients for individual vertices. Now, this means because each one of these clustering coefficients is between 0 and 1, the clustering coefficient of a graph is also between 0 and 1. And if the clustering coefficient of a graph is close to 1, we'll say a graph is highly clustered on average, whereas if it's close to 0, it's not highly clustered. So the clustering coefficient of a random graph turns out to be P, the probability, the expected degree, or the expected degree over the number of vertices. And this is practically 0 because K is much less than N. So random graphs don't tend to be clustered in the sense of the clustering coefficient. Now let's look at path length. So the shortest path length, or we'll call it simply path length, between 2 vertices in the graph G is the length of the shortest path between those 2 vertices. So let's look at some paths here between U and B. There's a path of length 4. There's another path of length 4. Here we have a path of length 7. But the shortest one is a path of length 3. And so therefore we would say that's the path length, or the shortest path length. We also might say it's the distance from U to V, and therefore a lot of times we'll write d u comma v as the path length or distance between the 2 vertices. So in this case the distance from U to V is 3. The average path length of a connected graph is the average over pairs of vertices of the path length. And we say that the distance between vertices is 0 if U is equal to V. So for example, 0, 1, 2, the path is just 2 steps long. We have 0 to 1 and 1 to 2 are both 1 step, 0 to 2 is 2 steps. So the average path length is 1 plus 1 plus 2 over 3, which is 4/3. If we go 0 to 1 to 2 to 3, the path of length, the path on 4 vertices, then we have 3 adjacencies. We have 2 that are 2 steps apart, and 0 to 3 is 3 steps. So that's 3 1s, 2 2s, and a 3 divided by 6, and that gives us a average path length of 5/3. Now, if we look at this graph in general, the path from 0 to n minus 1, you might see a pattern, and I'll let you think about that for your homework. Let's look at another example. This triangle, everything's connected to each other, and so the longest path is just 1. This cycle, the average path length is 2. This cycle, the average path length is 3. So again, you might notice a pattern. And again, I'll let you think about it. Now notice that the average path length has to be greater than or equal to 1, and the average path length can be huge. Now, the small world phenomenon is that there are many real-world graphs, G, that on average are highly clustered and tend to have nodes that are close to each other. So a graph is small world if both the clustering coefficient and the average path length are close to 1. For example, an airline network. It has short average path length because it has at most 2 or 3 flights to get to from one destination to another. It's highly clustered because most flights are out of only a few hubs. A gene regulatory network, the smaller LG is, the more quickly a cell, hence the organism itself, can modify its activity. The larger the clustering coefficient of the graph is, the more robust the cellular response to various stimuli. So let's look at an exploration of the small world phenomenon by 2 people called Watts and Strodos, and this was in Nature in 1998. Their motivation was that random graphs are not locally clustered and don't tend to have hubs. The degree distribution tends to converge to Poisson. So they started with a ring lattice of order n, and we're going to look at k even here. And we're going to, for each vertex, look at the k over 2 vertices on each side and make those neighbors of the given vertex. So here is a ring lattice where n is equal to 10 and k is equal to 4. And here's a ring lattice where n is 15 and k is equal to 6. Notice these are both k-regular graphs. Now we're going to introduce rewiring. For each node I and for each edge ij where I is less than j, with probability p for some fixed p, we replace ij with ik, where k is chosen uniformly from those vertices not equal to or adjacent to I. So if p is equal to 0, we just have our ring lattice. As p tends to increase, we start to see the graph become rewired. So we can say something theoretically at p equals 0 and p equals 1. So at 0, the average path length is n over 2k, which is very large because n is much greater than k. The 0 here refers to the ring lattice with probability p of rewiring, probability p equals 0 of rewiring. The clustering coefficient is 3/4 k minus 2k minus 1, and for a large k that's approximately 3/4. And notice this is independent of n. Now when we get to p equals 1, we get the average path length of a random graph. It's log n over log k, which is approximately 1. And we get the clustering coefficient is k over n, which is approximately 0. Now the fact that log n over log k is approximately 1, actually we're thinking in terms of orders of magnitude, and what we're saying is that n is much larger than k, but not many more orders of magnitude than k. So the n is just a few orders of magnitude larger than k in this sense. Now the average path length and the clustering coefficient for a ring lattice with rewiring with probability p, what we're going to do is we're going to do a trick. So we're going to divide LP by L0 and the clustering coefficient by clustering coefficient of 0. They're both starting at 1, both these ratios, obviously, and they both should end close to 0 as functions of p. But they behave quite differently. So what we're going to do is we're going to graph these simultaneously over 0 less or equal to p less or equal to 1, and we're going to have 1,000 vertices, and we're going to have k equals 10, and we're going to start with average path length of 50 and a clustering coefficient of 2/3. And because we take the ratios, notice that the clustering coefficient tends to go out for a while and then tail off, whereas the average path length tends to fall to 0 fairly quickly, where the lower axis is the probability p. So there we have at L of 0, and there we have at 0.01, and notice that the average path length has fallen quite a bit, but the clustering coefficient hasn't changed much. And then at 1, the clustering coefficient is very small, but the average path length is much smaller also. So graphs produced with values of p in the pink shaded area are highly clustered with a short average path length. The degree distribution is for p equals 0.01, the one we're looking at here, definitely not scale free. So let's look at an example. Let's think about Facebook. There are about 1 billion Facebook users and about 70 billion friendship links, which are the edges. And Twitter actually is very similar. The average shortest path length is 4. Now let's suppose that you and a randomly chosen other user are picked. He could be in China, or she could be in England. You're here in Johnson City, of course. Now, what does it mean to have an average shortest path length of 4? It means a friend of your friend knows a friend of their friend. So here's you, and here's your user that you've never met. They're in China or Russia or South America or somewhere. But you have a friend and they have a friend. And the fact that the average shortest path length is 4 means that they're friends. So on average, it's only 4 steps between you to somebody in England or Russia or China. That's called 4 degrees of separation. Another example let's look at is Facebook. There are about 1 billion Facebook users and about 70 billion friendship links. So Twitter is similar. So I'm just repeating what I said a moment ago, so you'll get the size, the order of magnitude here. So n here is very large. Now, I wanted to point out, so if you've got 1 billion Facebook users and about 70 billion friendship links, then that means that on average you're looking at a nearest neighbor k, or expected degree in some sense, of 7. So even though we have, 70. So even though we have n as 1 billion, we're looking at a k that's only about 70. High clustering coefficient. A high clustering coefficient is due to the existence of communities. A community is a highly connected hub, and communities tend to attract members of other communities, forming even bigger communities. And so when we talk about a graph being small world, we're really looking at this community structure that gives rises to connected communities that become even more connected and make even bigger communities. So a graph is small world if the vertices tend to be relatively close to each other and highly transitive, i.e. community structure, i.e. a high clustering coefficient. And typically we see a hierarchical structure, communities of communities of communities, and paths between different communities tend to be short. But notice, small world need not be scale free.